Yo! Welcome back to the Umi compiler dev series. Last time, we talked a little bit about fixed width built-in types, and we also talked about C-style strings, Pascal style strings. I also talked about kind of what I'm thinking about to do with structs, and we looked at different storage classes when it comes to internal variables, and also what I'm thinking about when it comes to data initializers and variable initializes, printfs, things like this. What we didn't do last time is we didn't actually write any code that would go ahead and start the compiler process altogether. So that's going to be the focus of today. We're actually going to write some code to make the compiler do some basic thing. Now, what that basic thing is what I want to talk about right now. So if you're new to compilers, and I'm not entirely an expert in it, but I know at least the basic things. And a compiler is usually split into different stages, right? You'll have the so-called parsing stage, maybe you have semantic analysis, and then at some point you'll have code generation. Before code generation, depending on the compiler, then you'll also have a stage of optimization as well. If you take a compiler course, or if you look at any of the compiler books that are available, then you'll see some breakdown that's similar to this. And the easiest thing to start off with, and also the thing that you have to start off with, is the parsing stage. Now, what is parsing? Obviously, whenever you write any source file, or if you write any text file that has human readable text, for the computer to be able to handle it, you need to be able to transform the characters of this file into something that's easy for the computer to understand. That, in a nutshell, is what's known as parsing. Now, for a compiler, the output of parsing is an AST, and an AST is an acronym for an abstract syntax tree. An abstract syntax tree sounds fancy. Essentially, all that it is it takes your source text, throws out things that are extraneous. For example, throws out comments, throws out white space, throws out things like semicolons, because that's not important to the compiler. It's only important for parsing to know when things begin and when things end. And the abstract syntax tree would encode the sort of flow of the program as it is written. So there might be a tree node for a function. Inside, there's going to be 1, 2, 3, 4, 5, 6, maybe 6 statement nodes. Each of those statement nodes would contain, say, type type modifier, storage class, name, a value given, if any, etc., etc. It's just breaking down the raw text of the program into something that the compiler can work with more directly. So that's where we're aiming, at least for the next little while, since parsing is, well, people talk a lot about parsing. And for this compiler, we're going to follow in the steps of Clang and GCC, and I think MSVC, and any sort of non-toy language, which is we're going to we're going to handwrite a compiler. It's going to be all of our own code. And the reason for using a custom parser instead of one that's auto-generated, and there are auto-generation tools like, what are they called again? Yak and Antler, or is it Antler? I think it's Antler. Antler 4. The reason why we're going to write our own thing is because a compiler isn't just a thing that takes code and raw program text and transforms it into executable code. We also care about errors, and I want this compiler to be super modern. So we want to have the highest quality of error messages, number one, but also I have other things I want to try out for this compiler when it comes to usability from the command line, and also interaction with consumers of the compiler data, IDEs, and things like this. So for that to be the easiest for us, and also the most performant, we're going to go ahead and we're going to write a top-down parser ourselves. So I think that's enough for a preamble. Let's just dive straight into it. So here's our main program. We before we write the parser, naturally, we're going to need to actually read in the source text. And I have some idea about how I want the compiler to ingest source files. Now, I talked a little bit before about how C and C++'s build system is incomplete, and I want to avoid that problem. So what I want is the compiler to be able, you just give the compiler, say, the name of this source file, and then it should be able to go through and infer the rest of the program structure from that single file. And how we're going to do that in the most flexible way so that it accommodates the widest number of use cases, we're going to explore later. But for right now, we at least need to be able to read in these source files. And I'm just going to hard set it so that the compiler will just look underneath this examples folder and it will just recurse down through any subdirectories and pick out any of the files that end in .umi. And it will just read those in directly. So let's do it. The first thing I'm going to do is I'm going to write main in my style. Get rid of you. Get rid of you. Excellent. So what I'm going to do is I'm just going to hard code in maybe the source root, the examples, like this. And when it comes to reading, when it comes to, okay, that does work. When it comes to reading in files, I'm sure you may already have heard about things like, what is it again? I believe these are inside of Unisted on my Mac here. Do we have open? Nope. It's not Unisted, it's probably fcntl. Yes. So you have things like open, openat, etc. However, when it comes to reading in a directory, opening a directory, reading the contents of a directory and doing tree walk, using open is a little too rigid for us. And POSIX, which is the portable operating system layer that Mac and Linux subscribe to, they come with another header file called dirent.h. And if we take a look-see inside, then it's kind of an abstraction layer over what the kernel sees as a directory structure. And unfortunately, POSIX is a little too light in specifying what should be inside of dirent. So if I'm not mistaken, and from my like very shallow testing on Linux, this dir directory has a different structure on macOS than it does on POSIX Linux. And because of that, we can't get away from using this header file. These function definitions, or these are prototypes, but these function declarations will be the same. However, the specific, you can see these are all pointers, right? The specific implementation of dir and its dirent structure as well, these are going to vary slightly between operating systems. So we can't just replicate the behavior and write our own stuff, which is a little sad because I don't like including these system header files if I can get around it. And the reason for that is because this header file will include other header files, which will include other header files, as you can see, and our poor like 9-line source file will blow up to like 20,000 lines, and it's just ridiculous. It's honestly ridiculous, and I don't like that. But in this case, we're not going to be able to get around it. So we'll just leave it the way that this is. Cool. Now, also, I have claim format here, but I don't think this is using my claim format. There it is. There we go. I think things are now going along formatting rules from claim format, so that's good. I like using 2 spaces because any more and it just gets crazy. The width is too big. When it's 2 spaces, it's more compact, and I don't know. I'm just used to using 2 spaces nowadays. But okay, so when we read in these files, we're actually going to need to store them somewhere. So I'm going to create 2 structures here. Maybe the first one we'll call module. We'll call module. You know what? We'll call it compilation module instead. Module is very generic, and I don't like the names being too generic. So compilation module is what we'll go with. And again, similar to Python, I think these each like UMI source file is a module, so it like defines its own namespace, and that is the same as Python, where you basically just interact with modules directly, and packages, which is a collection of modules. I'm not sure if we'll embellish in this language. For the time being, we'll just work off of a module basis. So what are we going to put inside of a module? Well, when it comes to iterating over source files and buffers and things like this, I usually follow this pattern where I have a source header struct sort of thing, and inside of it, I will have something like int, current, and I'll also have the bytes. And this is, for me, a pretty generic structure where we just have the current or the cursor where we are inside of bytes, the length or end for us, which is also an index, and bytes. Now, here we also will just stick this inside of here. So we'll call this source like this. Now, before we go any further, unfortunately, we have to tackle something head on right now, which is that in C and C++, int, the size of int is not guaranteed to be the same for every platform. In the spec for C, actually, int can be 16-bit or 32-bit. I haven't heard of a 64-bit integer platform, but I'm sure maybe one day that they will exist. But to combat this, in C99, they introduced C_student, and inside of C_student, you have the mins and the maxes, which are defined by the compiler, and you also get these type definitions, or these type definitions, more specifically, the fixed width type definitions. And I want to use these, but again, I don't like the idea of having to include C_student for a deficiency in the language. If I can, I want to define these myself. So that's what we're going to do. We're going to define the fixed width types ourselves, so that way we have complete control over what these type definitions mean. Also, we'll avoid annoyances between compilers where things will change size, or the specific width, the type which underlies the width, could change out from underneath us, and we'll see an example of that in just a little bit. But let's do this ourselves. Now, main.cpp, I want this compiler to be able to work on Windows natively, and also on Mac, and also on Linux, and whatever other platforms that exist. So what we'll do is we'll keep this file being we'll make this our POSIX. Platform layer. So all of the definitions and operating system level facilities that are inside of the POSIX spec, we'll write the code that will go inside of here. But for things that are platform independent, for example, compilation module, that is purely for us. Source iterator is also for us. This technically, I guess, is also for us. We'll stick these inside of a platform independent layer. So let's do that. I think I have, yep. So we'll create this header file. We'll pragma once it. Pragma once, if you're unaware, essentially the standards compliant way of creating a header file is that you would use if not defined thing, then you would hash define thing, and you would end with an endif, and you would put all of your declarations inside of here. And this is called a header guard. And this is completely standard, will work no matter where you are. But it's also 3 lines versus 1, and that's stupid, in my opinion. Pragma once is... We would have to use these pragmas for changing the default packing of structs. Also, pragma once is supported by basically all of the major compilers. So I don't particularly see any need to not use pragma once. So I'm going to use pragma once. Now, sea lion doesn't track header files unless those header files are included inside of a specific source file. So let's go ahead and we will include umi.h right here. Whoops. Do /umi. Okay. Very good. And let's take these and we will move them up into our new header file. Okay, awesome. Now, I don't think I've mentioned it in this project yet, but I'm a major fan of the Unity build or the single compilation build system. It's not really a build system, but like build philosophy for C and C++. If I go over it briefly, what it means is that for our specific build system here, we have CMake, which will go ahead and like generate a Ninja build file. We'd use make to do that, to build the actual things, and it decides where we stick all of our build artifacts. However, what most people do is that they will put here like add executable, and then they might do target add sources, and they'll target sources, sorry. They'll use target sources, and that would say like umi-posix, and then they might make it private, and then they would list of source files they would stick here. And it have, especially for a massive project like Google Chrome, you might have like 100 source files here, or you might split the CMake files across many different directories. And for me, that's just stupid. It's excessive mental overhead because we already have a system for including in build files, and it's hash include in C and C++. So the reason why you would use a Unity build is because you can just give the compiler one file. The compiler, as part of its hash include preprocessor search, would go and grab every other file that it needs, and you can avoid all of the headache of like, oh, we accidentally used an old version of the file, we used the wrong file for this thing, and it made a mistake, etc., etc. That's number one. Number two is you have pure like program optimization capabilities in C and C++, because the compiler can see everything inside of one compilation unit. If you use multiple source files for multiple compilation units, then you can only do global program optimization at link time, and I don't know. It seems like that's a suboptimal solution to the problem of we just need to be able to see all the source code at once, and so that's what the Unity build is for. Anyway, enough of the tangent. Let's talk about these fixed width types. So the way that the compiler knows what these are is, I think there's like the built-in, well, at least for Clang, and it doesn't look like C-Line has IntelliSense for it, but they have built-in types like maybe int16, or whatever they call them. The point is that either the compiler has intrinsics built in, or when the compiler distributes its standard library, they're written specifically with the knowledge of the platform, so that there's no inference of what the width of the types are. It's just hard coded into the compiler. For us, we don't have that leverage, so we're going to have to infer the width of the built-in types. And the way that we're going to do that is not with the preprocessor. We're going to do that with metaprogramming, template metaprogramming. It's a very C++ style solution. And essentially what we need is that we need to have a compile time if. And I'm going to call this if, like this. So it's a very generic struct template. Essentially, at compile time, we'll be asking a question, a true or false question, and we'll pass the answer to that through this Boolean parameter. If C is true, then we'll add in an alias here to be either true or it'll be false, depending on the question. And the way that you would do template metaprogramming for this specific case is we'll make the default answer to any question false, like this. And what we'll do is that we will use C++'s partial template specialization, which is a mouthful. But what that boils down to is we'll basically overload this struct definition for the specific case when C is true. Remember, C is knowable at compile time, so the compiler knows what the answer to this is. So when C is true, the compiler will choose this struct definition as the definition of if with these parameters. And when C is false, which is the other case, then it will choose this struct. And as you can see, if we're smart and we use the same internal type declaration using type equals true this time, however, then it's like we have a compile time function which returns a type like this. And what people often do, just to make this a little bit easier to use, is they will also create an alias for this. And they'll say like using if underscore t is equal to type name if of C, T, and F, whatever this is. Capture the flag for those people who get that reference. And because C++'s language rules are a little strange, whenever you use an internal alias like this, then you also need to include type name if the alias is in fact a type, which in our case it is. Okay. With our compile time if all ready to go, the way that we would use it is like this. So we can say using int 8, we're going to use the umi style built-in fixed with built-in types like this. So we'll use int8, uint8, byte8. Well, I'm not sure if I'll define these for the compiler, but we'll definitely define these two. We'll say int8. This is kind of an easy one. This is just signed char, because char is always going to be 8 bits on platforms people care about. Technically, in the C standard, char could not be 8 bits, but it's not 1970 anymore. So for most platforms, in fact, I think virtually all platforms, a char will be 8 bits, so we don't need to worry about that. However, where things get a little bit more interesting is int 16. So here is where we'll say if t, if the size of a short is equal to 2 bytes or 16 bits, then our int16 type will be assigned short. Else, it'll be assigned int. So on some platforms, probably from like the late 80s or early 90s, int was 16 bits long. However, when things went to 32-bit, CPU architectures became 32-bit, then short was designated to be 16 bits, and int was bumped up to 32 bits. So this will probably work, hopefully it'll work, on most platforms. At least this will certainly work on my Mac and also my other Windows testing boxes. So for the time being, we'll go with this. Next one, int32, we'll follow the pattern here. If the size of an int is equal to 4, which it should be, then this will be assigned int. Otherwise, this will be assigned long. In the same vein, back in ye olden days, a long used to be 32 bits. Although I think long can also technically be 16-bit. Not sure. But in the cases where int is not 32-bit, then we'll make int32 be a long. And finally, we'll use the same pattern, and we'll make it so that if the size of a long is equal to 8, then this will be assigned long. Otherwise, this will be long. So this is kind of the biggest case where we would need compile time ifs, because on Linux and Mac, long will be defined to be 8 bytes or 64-bit. However, on Windows, to this day, I believe, a signed long is still only 32 bits. And on Windows, a long is the only 64-bit size type. So that's important. Now we'll just follow this for the unsigned variants as well. So now I have to add un to everything. boom, and finally, boom, just like this. Okay. Those will be fine. I guess here, just for completeness, we'll also make this be signed, and here we'll say these will be unsigned. Excellent. Now, there's a few other types that I use quite often. One is size t. And for us, we will make size t be... Well, first, what is size t? Size t is the type that is returned by size of, technically. And to be honest, I'm a little weary about defining this because I know, without a doubt, from der end, size t is probably going to be defined from there as well. So I definitely can't. We're not going to call this size because size is... It looks like a variable name. So I'm a little wary about defining this, but just to show how you would do it. Size t is also generally the size of a pointer. So if the size of a pointer is going to be 4 bytes, then size t should be a uint32. Otherwise, we'll make this be a uint64. Now, one type I definitely want to have around as well is the signed size type. And in the same vein, this is going to be the same size as the pointer, but it will be the signed variant. I'm also in two minds whether or not we want to call these like type like this, or maybe we wanted this to be like sized. Not entirely sure. But for the time being, these will be, we'll define these here. If this becomes an issue because they're being double defined, which they might be, looks like it's okay. This might be an error on Windows at some point, because we've used... Well, actually, it could still be okay. I guess we'll see. But for the time being, we'll go with... Ooh, there was a typo there. Let's see. Will this still compile? Yes, it will. Cool. Okay, so, yeah, size t and size t, they'll be the size of an int. They'll be the size of a pointer, sorry. So when a pointer is size 4, then we'll use a 32-bit variant. When these are size 8, then these will be the 64-bit variant. Now, just because the pointer is equal to 4 doesn't necessarily mean that it will be equal to 8 in the false case, but what we'll do is we'll just skirt around that issue for now. And we'll just make sure at compile time that either the size of a pointer is 4 or it's going to be 8, one of the two. Okay. All right, good. Now that we have our fixed width types in, the final thing that we'll do is we'll go ahead and we will give these their proper typing. So I'm going to make current and end be 32-bit unsigned types. So our source file can be no bigger than 4 gigabytes, but I doubt that that's going to be a very big issue. And finally, our bytes won't be void star. I don't actually know why people use void star for things that they don't know the size of, because you can't do pointer arithmetic off void, right? A void pointer is when you don't know what the thing on the other end of the pointer is. So if you add 1 to a void pointer, it won't just increase the pointer by 1. It's meant to like scale based on the size of the thing on the other side of the pointer, but you don't know what that size is because it's void. So you always have to cast it to something. And that thing that you usually cast it to is an unsigned char. So I just avoid that whole headache and just make all of my kind of generic pointers be pointers to bytes, pointers to uint8s. And so that way we can just easily do pointer arithmetic. And whenever we need to make this be a specific type, then we'll just cast it at that point. Okay, awesome. Sweet. Okay, so we've got our fixed width types that we'll be using going forward. And as you can see, it's really not that difficult. Or I guess maybe because I've been doing this for a while, it doesn't seem that difficult. Template metaprogramming can absolutely go off the rails if you haven't done it for a long time, but hopefully at least this is a little easy to understand. But okay, that's basically all that I wanted to talk about today. Thank you so much for watching. If you have any questions, specifically, and maybe mainly around that template metaprogramming, then please leave your questions in the comments. And next time, what we'll do is we'll start writing code that will read in all of the contents from examples and all of the directories that are underneath it. But yep, can't wait to see you guys then, and have a great one. Ciao.